a lot of times in the real world, we have some function, for example, the cost of renting a U-Haul truck, and that function is going to have an output that depends on multiple inputs. So in the case of renting a U-Haul truck, you're going to need to consider how far you're going to drive it, how many miles you'll put on it, as well as how many days you're going to rent it for. And those two things will help you estimate your total cost. So when we talk about a multivariable function, you might think, well, why isn't y equals 3x plus 2 a multivariable function? Why is that what we call single variable function? Well, it's a single variable because the single refers to the number of inputs, and there is only one input and one output. When we call something multivariable, the assumption is that we have more than one input and only one output. Okay, so that's going to be a multivariable function. Now, we've seen before that something like y equals 3x plus 2, that we could say y is f of x, and all we mean by that is that the value y is a function of x. It depends on the value of x. How is it computed? Well, it's computed by taking 3 times the value of x and adding 2 to that result. And sometimes we use these interchangeably. We may say y equals 3x plus 2 like we did up here, or we may say f of x equals 3x plus 2. That is the function of x, and f of x is just another way to say y. So when we incorporate more than one input variable, like in this example, z is equal to f of x and y, you can see the only difference is that now we're going to have more than one input separated by commas as the argument into this function. So z, this variable z, its value is a function of 2 inputs, x and y, and we can write that function in one of 2 ways. We could say z is calculated by taking twice x and subtracting thrice y. That's right, I said thrice y. Or you could write f of xy equals 2x minus 3y. And those would be the same way of writing it. The reason we prefer to use f of xy is that if I plug in a value for x and y, I can say, for instance, f of 1 comma 5, well, that would require me to plug in 1 for x and 5 for y. So notice that we do need to know, the order in which these variables are being described. It doesn't have to be f of xy, it could be f of y comma x, but the user of the function has to know distinctly which one of the two it is, right? So that the user knows that the first value goes in for x and the second value goes in for y. So in this case, when we evaluate this, 2 minus 15 is negative 13. And so it's much more convenient to just say f of 1 comma 5 equals negative 13, as opposed to plugging in 1 for x and 5 for y and just saying z equals negative 13 and having then write when x equals 1 and y equals 5. It's much neater to write it like this. So we're not limited to f, right? We could call f is just the name of the function. F is a nice letter to use, but we could have g of xy. And the reason I say that is because here we have this function g of xy. And we've all probably seen over the course of our education that even a function like y equals 3x plus 2, this analogy of this black box that converts inputs into outputs, right? So you feed in an input x, and what it outputs is a value of y, according to the rule. So in this case, the rule is 3x plus 2. Over here, we're saying that there's just some function g that takes 2 inputs, right? It has to take a pair of values, a pair of inputs. And because g is a function of 2 inputs, it's then going to output something. Well, in this case, it's going to, for this particular example, we're going to output the square of x and add it to the square of y. So right here, if we give this black box an input pair of 2 and -1, well, that means that what's going to get computed is 2 squared plus -1 squared, which is 4 plus 1, which is 5, and that's what's going to come out of this function. So this is just a way we could sort of diagrammatically visualize what it is that's going on. We give the function a pair of values, it outputs a single number. And multivariable, because of there being more than one input and only one output. Let's take a look at an example where we have a real-world context. You own a company that makes 2 models of speakers, the Ultra Mini and the Big Stack. Your total monthly cost in dollars to make X Ultra Minis and Y Big Stacks is given by C. Okay, in this case, we're not calling it G or F, we're just saying C of X, Y, which is convenient to stand for cost as a function of how many Ultra Minis and Big Stacks, and it's equal to 10,000 plus 20X plus 40Y. Okay, what's the significance of each term in this formula? Well, let's think about this. If I were to give you a value, like for instance, let's just look at C of 0, 0. So what would be the cost if I were to produce 0 of each? Well, that means that X and Y are both going to take on a value of 0. And the only non-zero quantity is this 10,000, and so my total cost will be 10,000. How could I have cost if I didn't make any speakers? Well, I probably still have a factory or some place that I have to pay for electricity and bills, and maybe I have employees. And so this is sort of the fixed cost of operation. Now, what we actually call this, you might recall from functions like y equals 3x plus 2, just to give sort of this two-dimensional analogy to what we're doing now. If I look at that function right there, and better yet, let me call it f of x, and I give this an input of 0, I get 3 times 0 plus 2, and this gives me the ordered pair 0, 2. And that value, too, is what we would often refer to as the vertical or y-intercept. Okay, now in this case, we plugged in 0 for both inputs, and what we're going to call this is often called the z-intercept. So the z-intercept would be the value out of the output when both inputs are 0. Okay. Now, it's really not even fair to call it a z-intercept because that assumes that you have x, y, and z, but that's the phrasing we might often give this, is that value corresponds to the z-intercept. The z-intercept is actually the ordered triple, but this is the output of that ordered triple. Now, what else could we say? Well, let's think about this. So every time I increase x by 1, let's compare this to only changing the value of x, right? That way I can see how much my cost changes by for 1 unit of the Ultra Mini. So 20 times 1 plus 40 times 0. That's going to give us $10,020. Well, the only thing that's changed is that I have increased x by 1, so the change in x equals 1. The change in cost is equal to $20, and if you increased it to 2, it would be $10,040. And so the ratio of the change in cost to the change in x is 20 over 1. Or in other words, I could say, by doing the unit investigation here, cost is measured in dollars, x is measured in Ultra Minis, so I could say that the cost is $20 per Ultra Mini. So this is a rate of change or slope in the x direction. Okay, so only changing the value of x, we get a change in cost of $20. We can make a similar argument for y. It'd be the same thing, it'd just be 40 times 1, and we could see that the change in cost for each big stack is going to be $40 per one big stack, and that is the slope in the y direction. That's how we say this, right? That's y direction because you have two rates of change, one associated with changing x and another rate of change associated with changing y. So you have two quantities of change causing change. You have ultra minis and you have big stacks, both of which uniquely affect the cost. And we can kind of see that this is looking a lot like a linear function in that if you increase x by 1, you get a constant change in cost. You increase y by 1, you get a different, but you still get a constant change in cost, regardless of how many units have already been manufactured. So it's going to cost you $40 for each additional big stack. Now, we can also think about the kind of the domain, if you will, or the input space, the set of all possible inputs that we can give this function. And so because this has two inputs, x and y, I kind of have to think about a reasonable interval of values. So I'm going to kind of try to, and we don't know much about this company, we don't know much about what they're capable of, but let's just say we learned that they can only manufacture up to 100 of these ultra minis per day. Well, they can't produce fewer than 0, so it has to be, x has to be bigger than or equal to 0, but less than or equal to, we'll just say 100. And we'll say that maybe for the big stack, they can only produce 50, so maybe this is going to go from 0 to 50. What I'm going to do is I'm going to draw an xy plane. This is called an xy plane. XY plane, right? Because it's a flat surface that has two axes, namely x and y. And now I can sort of think about x is going to go from 0 to 100. We'll say that's about there. And y is going to go from 0 to 50. We'll say that's about there. So basically, the inputs that I could give this function are any ordered pairs between 0 and 100 and 0 to 50. So it's not sufficient just to state the interval of values just for x. We also have to do the same thing for y. Now in here you can kind of imagine that since we're selling units of something, that it's not every single point in here. It would just be all of the integers from 0 to 100, right? And we could have maybe this represents 25, and then this is 125, and then maybe this is 225, and this is 325. And so this just describes that input space that we can select ordered pairs from if we assume that this is a reasonable domain. So each of these ordered pairs in here has a cost, right? That guy has a cost of, if we call that, I don't know, we'll say, again, 3, 25. And this guy has its own cost associated with cost of 2, 25. And this one here, cost of 1.25, etc. So there's each of these ordered pairs in here has a output, just like we've described here. Every time we select a new ordered pair, it's going to generate a different value. Now we've already kind of discovered this, and here's where we'll stop with this, just introducing these ideas. A function f of n variables is linear if it has the property that, okay, well in this case, this has 1, 2, 3, 4, 5. I don't know how many variables it has. We'll just say it goes up to n variables. So it could be 10, it could be 20 variables. But it's going to have some z-intercept, which is going to be this guy, a0. And then notice that what we have here is this is the slope in x1 direction. And then you have the slope in the x2 direction, the slope in the x3 direction, and this is the slope in xn direction. So for example, if I told you that I added a unit of, I have the ultra mini, the big stack, and we'll just say that this is the the big kahuna, then let's suppose that that was 10,000 plus 20x plus 40y and maybe plus this one is going to cost me a little bit more to manufacture. You can still see that that's a linear function. Every time you increase z by 1, the cost of the big kahuna, that's going to be the slope in the z direction. So the change in cost for each additional big kahuna will be $60 per one big kahuna. With all this said, when we're investigating multivariable functions, it's a lot of the same concepts from single variable functions, except now we have this idea of another input, and how we have to visualize this changes a little bit, because it's not just two quantities that we have changing anymore. We have two inputs that are changing, which then affect the output. So, as a little bit of foreshadowing, instead of having 2 dimensions, we're going to need 3 dimensions. So imagine that this xy plane is actually here. Maybe it looks like this. There's y, there's x. So you can kind of see if you rotated this y-axis up, boom, it would be the y-x. And then here you have a cost associated with that. So if we figure out how many units we have, maybe, again, 1, 2, 3 units of x, and maybe 1, 2, 3, 4 units of y, then we have some sort of cost associated with that, which will be the cost of 3 units of input and 4 units of the other input.